Dear students, now we are going to learn about subgroups. In the previous module, we have defined the structure of a group and learned some examples of groups. Among our examples of groups in module 1, we have seen that the group of integers under addition is a subset of the group of real numbers under addition. Similarly, the subset 1 minus 1 I minus I of the complex numbers is a group under complex multiplications. This situation arises so often that we introduces a special term to describe it, that is called subgroup of a group. Let us see the definition of subgroup. The definition of subgroup: let G multiplication be a group. A subset H of G is called a subset of G if H also form a group under the operation multiplication. We use the notation H is lower or equivalent to G to mean H is a subgroup of G. If we want to indicate that H is a subgroup of G but not equivalent to G itself, we write H is lower than G. Such a subgroup is called a proper subgroup. The subgroup E is called the trivial subgroup of G. A subgroup that is not E is called a non-trivial subgroup of G. Let us see some examples for subgroup. Let G be a set of all non-zero complex numbers and G is group under complex multiplication. Then the subset H is equivalent to 1 minus 1 I and minus I of G is a group under complex multiplication. Therefore, H is a subgroup of G. Let G be set of all real numbers and G form a group under addition. Let H be set of all rational numbers and H form a group under addition. Then H is subgroup of group G. When determining whether or not a subset H of a group G is a subgroup of G, one need not directly verify the group axioms. The next three results provide simple tests that suffice to show a subset of a group is a subgroup. Let us see the result 1 first. One-step subgroup test. Let G be a group and H is a non-empty subset of G. Then H is a subgroup of G if H is closed under division, that is, if AB to the power of minus 1 is in H whenever A and B are in H. We can prove it by, given that G is a group under H is non-empty subset of G. Since the operation of H is the same as that of G, it is clear that this operation is associative. Next, we show that E is in H. Since H is non-empty, we may pick some X in H. Then, letting A is equivalent to X and B is equivalent to X, in the hypothesis we have E is equivalent to X into X to the power minus 1 is in H whenever X is in H. All we need to do is choose A is equivalent to E and B is equivalent to X in the statement of the theorem. Finally, we show that H is closed, that is, if X, Y belongs to H, we must show X, Y is in H also. Well, we have already shown that y to the power minus 1 is in H whenever y is, so letting A is equivalent to x and B is equivalent to y to the power minus 1. We have xy is equivalent to x into y to the power minus 1 the whole power minus 1. That is again equivalent to a b to the power minus 1 is in H. Thus, H is a subgroup of G. Let's check one-step subgroup test for even integers. For example, consider the subset E of even integers in the group of all integers Z under addition. Let A is equal to 2n and B is equal to 2m be two elements in E. Then A minus B is equal to 2n minus 2m, that is again equivalent to 2 into n minus m, which is also an even integer. So, E satisfies the one-step subgroup test. Therefore, the set of even integer is a subgroup of the group of all integers under addition. The second test is two-step subgroup test. That is, let G be a group and H a non-empty subset of G. Then H is a subgroup of G if A, B is the element of H whenever A, B is element of H. That is closure property. And A to the power minus 1 is element of H whenever A is an element of H, that is inverse property. We can prove it now as given that G is a group and H a non-empty subset of G. By the result 1, it suffices to show that A, B is element of H implies A, B to the power minus 1 is element of H. So, we suppose that A, B element of H, since H is closed under inverse. We also have B to the power minus 1 is element of H. Thus, A, B to the power minus 1 is element of H by closure under multiplication. Hence, H is a subgroup of G. Let's see one example for two-step subgroup test. Let G be an abelian group under multiplication with identity E. Consider the subset H of all squares, that is H is equivalent to x square, x is element of G. We are going to show that H forms a subgroup of G. Clearly, E square is equivalent to E. So, the identity has the correct form. Next, we need to write two elements of H in the correct form. Let A square and B square is in H. We must show A square into B square the whole power of minus 1 also has the correct form. Since G is a abelian group, we may write A square into B square the whole power of minus 1 as AB to the power minus 1 the whole square, which is the correct form. Thus, H is a subgroup of G. Third test is finite subgroup test. It says that let H be a non-empty finite subset of group G. Then H is a subgroup of G if H is closed under the operation of G. We can prove it as given that H is a non-empty finite subset of a group G. To prove that H is a subgroup of G, by the result 2 we need only prove that A to the power minus 1 is element of H whenever A is an element of H. If A is equivalent to E, then a to the power minus 1 is also equivalent to a. If a is not equivalent to e, consider the sequence a square, a cube and so on. Since H is finite and closure implies that all positive powers of A are in H and all of these elements are distinct. Say A to the power I is equivalent to A to the power j and I is greater than j. Then A to the power I minus j is equivalent to E. And since A is not equivalent to E, I minus j is greater than 1. Thus, a to the power I minus j is equivalent to a dot a to the power I minus j minus 1 is equivalent to E. And therefore, a to the power I minus j minus 1 is equivalent to a to the power minus 1. But I minus j is greater than or equivalent to 1 implies a to the power I minus j minus 1 is element of H. Therefore, H is a subgroup of G. Let us verify it for a subset of integer modulo 10 under addition. For example, consider the subset H is equivalent to 0, 2, 4, 6 and 8 in the group of integer modulo 10 under addition. Clearly, sum of any two even integer is again an even integer and the remainder when dividing the even integer with 10 is in H. So, integer modulo plus of any two element in H is in H. Therefore, H is closed. Thus, by finite subgroup test, H is a subgroup of integer Z of 10. How do you prove a subset of group is not a subgroup? Here are three possible ways. Let us see one by one. First one, show that the identity is not in the set. Second one is, exhibit an element of the set whose inverse is not in the set. And the third one is, exhibit two elements of the set whose operated element is not in the set. Here are some examples which are subset of group but not a subgroup. Set all of positive integers Z plus under addition is not a subgroup of group of integers Z under addition because although Z plus is closed under plus, it does not contain the identity O of Z. Let R be the group of non-zero real numbers under multiplication. Let H be the subset of real numbers greater than or equivalent to 1. That is, H is equivalent to X is the element of R which is proportional to X is greater than or equivalent to 1. Then H is not a subgroup of R since 2 is the element of H but 2 to the whole power minus 1 is equivalent to 1 by 2 is not an element of H. Let R be the group of non-zero real numbers under multiplication. Let K be the set of irrational numbers in R together with 1. That is, H is equivalent to X is the element of R which is proportional to X is equivalent to 1 or X is irrational. Then H is not a subgroup of R since root 2 is the element of K but root 2 into root 2 is equivalent to 2 is not the element of K. The set of non-zero integers under multiplication is not a subgroup of the group of non-zero real numbers under multiplication because the multiplicative inverse of 2 is 1 by 2, that is half, which is not an integer. Notice that Z of n under addition modulo n is not a subgroup of Z under addition, since addition modulo n is not the operation of Z. In the last module, we learned that identity of a group is unique. If it is unique, then what will be the identity of the subgroup? Let us see the first result. The identity of a subgroup is the identity of the group. That is, if G is a group with identity E and H is a subgroup of G with the identity E of H, then E of H is equivalent to E of N. We can prove it by let H be subgroup of group G, let multiplication be the binary operation of both H and G. Let E of H, E of G be identities of H and G respectively. Since H is less than or equivalent to G, E of H is the element of G. So, E of H is an element of G and E of G is the element of identity of G. Therefore, E of H is equivalent to E of G, that is again equivalent to E of H. Since E of H is equivalent to E of H and again equivalent to E of H, we have E of H is equivalent to E of G, which is again equivalent to E of H into E of H. Now, by cancellation law, E of G is equivalent to E of H. Now, think about inverse element of a subgroup. Now, we shall see about the result too. The inverse of an element in a subgroup is the inverse of the element in the group. That is, if H is a subgroup of a group G and A and B are elements of H, such that AB is equivalent to BA, that is again equivalent to E of H. Then AB is equivalent to BA, which is again equivalent to E of G. One another main thing in a group is generator. Let's see what is generator. Let G be a group and let A be any element of G. Then the set generated by the element A is element of A, which is equivalent to A to the power of n, which that is proportionate to n is the element of Z. Always A to the power 0 is defined to be the identity. Is generator of an element can be a subgroup? Yes, it is. Let us see, element of A is a subgroup. Let us prove it here as let A to the power n and A to the power m is an element of A. Then A to the power n into A to the power m the whole power minus 1 is equivalent to A to the power n minus m is the element of A. So, by one step subgroup test, element A is a subgroup of G. Thus, we call the subgroup element A by the subgroup generated by the element A. Here, there are some examples of generators. Let us see one by one. In the integer Z of 10 under modulo multiplication, 3 is equivalent to 3, 9, 27, 81 and so on, because 3 to the power 1 is equivalent to 3, 3 to the power 2 is equivalent to 9, 3 to the power 3 is equivalent to 27 and 3 to the power 4 is equivalent to 81 and 3 to the power 5 is equivalent to 243 and so on. The second step is in the integer Z, 2 is equivalent to 2, 4, 6, 8 because 2 to the power 1 is equivalent to 2, 2 square is equivalent to 2 plus 2 is equivalent to 4, and 2 cube is equivalent to 2 plus 2 plus 2, that is equivalent to 6, and 2 to the power 4 is equivalent to 2 plus 2 plus 2 plus 2 is equivalent to 8, and so on. Remember, a to the power n means na when the operation is addition. In the third step, in the integer z, minus 1 is equivalent to minus 2, minus 1, 0, 1, 2, and so on, that is equivalent to z. Here, each entry in the test up to 2 into minus 1, minus 1 into minus 1, 0 into minus 1, 1 into minus 1, 2 into minus 1, and so on, represents a distinct group element. Next, we can see one of the most important subgroups called center of a group. Definition: center of a group. The center of G of a group G is a subset of element in G that commute with every element of G. In symbols, Z of G is equivalent to A is an element of G divided by AX is equivalent to XA for all X in G. The notation center of G comes from the fact that the German word for center is Zentrum. There are some results based on center of a group. Result 1. Center of G contains the identity element of G. We know that every element in an abelian group commutes with each other. So, center of an abelian group is the entire group. More specifically, a group G is abelian if and only if center of G that is equivalent to G. Let's find out the center for upper triangular matrices of the form. You can see it from the board. Example, consider the group G of all 3 into 3 upper triangular matrices of the form from the board. Please watch the board, where A, B, C are integer under the operation of matrix multiplication. Please view the board. Next, we are going to prove center is a subgroup. Theorem: the center of a group G is a subgroup of G. We can prove it here as, let G be a group and center of G is a center of a group. Clearly, E is the element of center of G, so center of G is non-empty. Now, suppose A, B is a element of center of G, then by commutative and associative property, we have AB into X is equivalent to A into BX, that is again equivalent to A into XB, which is again equivalent to AX into B is equivalent to XA into B, which is again going to be equivalent to X into AB for all X in G, and therefore AB is the element of center of G. Next, assume that A is the element of center of G, then we have AX is equivalent to XA for all X in G. What we want is A to the power minus 1, X is equivalent to X into A to the power minus 1 for all X in G. Now, pre and post multiply by A to the power minus 1. A minus 1 into AX into a to the power minus 1 is equivalent to a minus 1 into xa, a to the power minus 1. By associate law, a to the power minus 1 into a to the power minus 1 is equivalent to a to the power minus 1 x into a to the power minus 1. E into a to the power minus 1 is equivalent to a to the power minus 1 xe. Xa to the power minus 1 is equivalent to a to the power minus 1 into x. This shows that a to the power minus 1 is the element of z of g. Whenever a to the is element of z of g, hence the center of a group G is a subgroup of G. Although an element from a non-abelian group need not necessarily commute with every element of the group, there are always some elements with which it will commute. This observation prompts the next definition. Definition of centralizer of A in G. Let A be a fixed element of a group G. The centralizer of A in G, that is A of G, is a set of all elements in G that commute with A. In symbols, A of G is equivalent to G is an element of G by GA is equivalent to AG. One another main result is G of A is subgroup of G. That is, for each A in a group G, the centralizer of A is a subgroup of G. Let us find out GA for some elements in 2 into 2 non-singular matrices over integer 2. Example, consider the group G of all 2 into 2 non-singular matrices over integer 2 under matrix multiplication. Then G contains the 6 elements. You can view it from the board. Finally, let us see some of the main results in subgroups. First one is theorem. Let G be a group and let H and K be subgroups of G. Prove that H and K is also a subgroup. Now we can prove. Since H and K are subgroups, then E is the element of H and E is the element of K, implying that E is the element of H and K. Now let A, B is the element of H and K. This implies that A, B is the element of H, and since H is a subgroup, then A is equivalent to B is the element of H and A to the power minus 1 is the element of H. Likewise, A, B is the element of K, and since K is a subgroup, then that A is equivalent to B, element of H and K, and A to the power minus 1 is the element of H and K. Hence, by two-step subgroup test, H and K is a subgroup of G. Final result is the theorem. Let G be an abelian group and let H is equivalent to A is the element of G and A to the power 5 is equivalent to E. Prove that H is a subgroup of G. Subproof. The identity element is trivially a member of H since E to the power 5 is equivalent to E, making H a non-empty set. To show closer, let A, B is the element of H so that A to the power 5 is equivalent to E and B to the power 5 is equivalent to E. Since G is abelian, we have that A is equivalent to B to the power 5, which is again equivalent to A to the power 5 into B to the power 5, which is again equivalent to E into E, that is equivalent to E. So, A into B is element of H. The inverse element is in H because A to the power minus 1 the whole power 5 is equivalent to A to the power minus 5, which is again equivalent to A to the power 5 the whole power minus 1 is equivalent to E to the power minus 1, which is equivalent to E. So, we have shown that H has an identity element, is closed under binary operations and has the inverse element. Hence, by two-step subgroup test, H is a subgroup of G. Students, now we can conclude this chapter, that is subgroups in model algebra, with a well-effect manner. I hope that you have all well done in this chapter. Thank you.